This is step 2, 2016, question 8. This question wasn't particularly tricky, in my opinion. It was fun to do, but honestly, the part two, well, not the part two, the final part of part two, this part, I'm gonna be real with you. I got cooked. I literally got cooked. Albeit I was outside when I was doing this question. I was walking, so I was trying to do it in my head. So I had to go to the mark scheme, and for literally this is like the first time in ages I had to go to the mark scheme, and I was low key disappointed in myself. I was like, how has this happened? But I had to go to the mark scheme, and I had to look at you know what the hell do you do here? And what ended up happening was, well, the mark scheme didn't even, well, it gave me maybe one hint, but it didn't really end up doing anything for me. So I got home and then I looked at the question again, and I did it on my tablet, and I finally got it. So maybe if I was at home and spent enough time on it, I maybe would have gotten it, but I still doubt it because um, I don't know. I did have a small hint from the mark scheme, which I didn't have earlier. But the sad thing is that literally this part two, or the final part of this part two, is actually like 4 marks. So you can easily get 16 on this question. Um, well, not super easily, but you can. I think that the first 16 marks are very accessible. But anyways, enough of my yapping. Let's just get into it. So this let's first just evaluate this integral, right? This is obviously just corporeal two further mass. I don't know because it's step two. I don't think corporeal two topics are covered, so I guess you're not supposed to know how improper integrals kind of work. But I think regardless, it's still quite. I hate saying this word, but I think it's quite trivial. Doing, um, you know, knowing that 1/infinity goes to zero, so it's fine. But yeah, it's not really technically part of AS further mass because that's the content that's assessed in step two. But yeah, okay. Just for good notation, we're going to write the limit of t goes to infinity or t approaches infinity, and then that just ends up going to this. Cool. Right. If you just evaluate it, you'll get one minus 1/t, which is just zero because it's 1/infinity, plus 1/m minus a half, which goes to this. I didn't spend much time on this because I think it's just evaluating an integral, right? But yeah, okay, cool. The next part, now, this sketch, right? I'm gonna just write that the integral is equal to this, just to keep the information, right? Because information in step is always quite handy. Anyways, show by means of a sketch that we can approximate this summation as we can show that this summation is approximately equal to this integral. Okay, or vice versa. Anyways, so what we want to do is we want to first draw the graph of 1/x squared. Okay. Now, if they've given you an upper limit and a lower limit, and they've given you a summation, or sorry, they've given you an upper limit and a lower limit of a integral, and they've given you a summation, and they're telling you to draw a sketch, they probably want you to consider area, right? Because obviously we have to draw a graph. They've given us a summation. We have an integral. An integral is just the area under a curve, so we probably do have to consider the area, right? But I think the difficulty of this question lies in. Sorry, that's like the worst 1/x squared graph you're ever going to see, but whatever. Um, I think the difficulty of this question lies in, or this part of the question kind of lies in what you do with the information given, right? You have n minus a half and then you have n plus a half. So you were like, okay, what the hell do I do? But I think it really helps if you just first of all evaluate the first few terms of a summation. And I think this is one of the best tricks, right? Because if you ever have a summation, just plug in the first few terms always, just to kind of see what result you're trying to expect or what you want to force your result to be. So our first term is going to be 1 plus m squared, 1 plus 1 over m plus 1 whole squared, and we're going to end up finishing on 1 over n squared, right? This is the summation of r is equal to m to n of 1 over r squared, right? Now, if we look at this graph, obviously our starting limit is going to be m minus a half, and our final limit is going to be n plus a half. Now, if we're considering areas and there's an approximation, we probably want to separate this integral, but like this whole area here, right, into some shape, into mini shapes. And I think the reason we're giving this approximation is to kind of separate it into a shape we know. And this in this circumstance, I think it's best to do a rectangle. I know it's probably tempting to do a trapezium, but I think a trapezium would end up just kind of complicating it. And a rectangle works really nicely because you have m minus a half for a reason, right? And I'll show you why now. Why we have m minus a half, and it's because we want the second side of the triangle to be m plus a half, and we want it to be m plus a half because then this side here becomes 1, right? And obviously we have multiple rectangles, okay, and we all want them to have sides a width, of 1, where these all are going to have widths of 1. And now it's tempting to kind of make the height of this triangle 1 over m minus a half whole squared, but that doesn't really lead you anywhere. What you should do instead is you should make the height of the triangle 1 over m squared, right, and consider the midway point as the x-coordinate, the midway point between m minus a half and m plus a half as your x-coordinate, and therefore your y-coordinate, which is your height, will be 1 over m squared. Sorry if I've explained that badly, but we basically essentially want each one of these areas here of these rectangles to correspond with each term of the summation, right? So if we make the height here 1 over m squared, so that our rectangle is going to look something like this, right? It's not entirely exact, right? It will look something like that. So our first one is going to be our first area is going to be 1 over m squared, which corresponds to the first term here. And what you realize is this integral from m minus a half to n plus a half, right, of 1 over x squared dx is approximately going to be equal to the area of all of our rectangles, right? Okay. Now, this is the first rectangle. Now let's look at the last one because doing the middle ones is just going to be too much. But let's just consider the last one, right? If we call this side here n minus a half, because our final side is n plus a half, this will have a width of 1, and we make our height 1 over n squared because we're going to take the midway point between these two sides, like I said earlier, as our x-coordinate, and then make that, obviously plug that into our function to get the height. Then our final rectangle is going to be 1 over n squared, which conveniently is our last term of this summation. So therefore we can just say that the summation of all of these terms, which is essentially the summation of all of these rectangles, which will mean that that this integral is approximately equal to the summation of r is equal to m to n of 1 over n squared. I hope that makes sense. If it doesn't, pop the comment and I'll try and explain it a bit better in the comments. But yeah, so that's that one. Now, okay, for part one, well, now this was like the STEM part of the question. Now let's get into like the actual real part of the question, I guess, or the real part one. I don't know. Anyways, we're given that the infinite series from 1 to infinity, the summation of the summation of 1 over r squared from 1 to infinity converges to a value called e, right? And we want to obtain these following approximations. Okay, cool. So, of course, we're going to have to use the part before, or the part we just proved. So, if we take maybe, if we take now, let's just say the lower limit of, let's just say m equals 1, right? So we want to find an approximation for this. Okay, we want to find an approximation for this. Now, if you notice here, our m value is 1 and our n value is infinity. So we can approximate this into an integral of from 1 minus a half to just infinity, because I mean it's infinity plus a half, but infinity plus anything will just end up being infinity anyways. So of 1 over x squared dx, which, if we go back to our result here, we don't even need to evaluate the integral. We just plug in 1 into this value of I. I called it I because I like calling all my integrals I. But yeah, we established in the very, very first part of this question that this integral from m minus a half to infinity just goes to this, right? So we just plug in m equals 1, and then you end up getting that this just, our value of e, we get the first value of e to approximately equal 1 over half, which equals 2, which is the first approximation, okay? So let's call this approx 1, okay? Now let's look at the second approximation. Now, we know that is equal to of 1 over r squared. It's also equal to the summation from r is equal to 1 to, 1 in itself, just the 1 of 1 over r squared plus the integral, plus the summation from r equals 2 to infinity, right, of 1 over r squared. But we can further approximate this into plus the integral from 2 minus a half to infinity of 1 over x squared dx. And that's approximately equal to e, which, so it's just 1 plus 1 over 2 minus a half, which just ends up being 5 over 3. So this is equal to approximation 2, which is exactly what we needed to do. And you can kind of see what the pattern is, right? We obtain like an accurate value using the summation, and then we use the next few terms to calculate our approximate value, and we add them, right? And so we're just going to do for the same for approximation 3. We're just going to take the summation now from, instead of r equals 1 to 1, or approximate straight from r equals 1 to infinity, we're going to take it from r equals 1 to 2, and then we're going to approximate from 3, the term 3 onwards, with the integral, because that's what we can do. So cool. Again, don't have a lot of space, so I think I'm going to delete the earlier working. Yeah, probably going to delete the earlier working. Sorry. Because I just don't want to have to scroll down too much to the page, because I want to keep the question kind of visible. But if you need to screenshot, do screenshot. Cool. Okay. So, like I said, we've approximated from r equals 1 onwards. Then we approximated from r equals 2 onwards, but added the accurate value from r equals 1. And then we approximated from, now what we're going to do, is approximate from r equals 3 onwards, and add on the values of 1 and 2 from the accurate summation that we're given. So what we're going to do is the summation of 1 to 2 of 1 over r squared plus the integral from 3 minus a half of 1 over x squared dx, or 3 minus a half to infinity, is approximately equal to our third value of e, called it e3. And this will just be 1 plus 1 over 4 plus 1 over 3 minus a half, which is equal to 5 over 4 plus, this is going to be 6, I think it'll be 5 over 2 over 5, which ends up going to 33 over 20, which is equal to approximation 3. So now we have approximation 1, approximation 2, and approximation 3, which is exactly what we needed to get. So cool. Not too hard in my opinion. I think even if you're kind of stuck, you can just kind of, over time you'll just see, right? Like if you're staring at this question for long enough, you'll just see, okay, we're given 3 approximations, so we probably need to manipulate the thing we've just proved in different ways, right? Because we're given a summation and an integral, so it probably makes sense to try and take some values out of the summation and then some values, and then approximate further with the integral, if that makes sense. Okay. Nice. I'm gonna get rid of this, all of this. Sorry. Again, I just need to save space. Cool. But I'm gonna keep note of the approximations. Okay. Cool. Show that when r is large, the area in approximating 1 over r squared by r minus a half and r plus a half of 1 over x squared dx, the integral of 1 over x squared dx, is approximately 1 over 4 r to the 4. Okay. So remember when we were just doing rectangles? Maybe I shouldn't have deleted the graph, I'm sorry. But remember when we were finding the rectangles, right? Maybe I'll redraw it. Okay. When we were drawing the rectangles, if we just take this to be r, because we want r to be large, so let's just take this to be r, right? Remember how our penultimate sort of x coordinate of the side was r minus a half, and the final one would be r plus a half. So essentially, what it's doing, it's asking us for the error of one strip of one rectangle area that we calculated in the part one where we sketched. So it wants us the error of this, because what you're going to see, right, is that there's going to be some error, which is the shaded area, right? Because the integral obviously covers the whole area bounded underneath the curve, and the rectangle is just going to cover this area here, which is the horizontal shaded lines I've just drawn now. And obviously, from what we've just done earlier, the area of this rectangle is just 1 over r squared. Okay. So 1 over r squared is equal to area of one rectangle. And now what we want to do is integrate this curve between r minus a half and r plus a half to get the total area bounded by the curve between that rectangle, between the sides of that rectangle. So what we're going to get is, well, we already know what this integral goes to from, well, we know that this integral is going to go to this, right? If you just, because the integral of 1 over x squared is just minus 1 over x. And then if we go further, we're going to get minus 1 over r plus a half plus 1 over r minus a half, which is actually just equal to 2r over 2r minus 1. Sorry, not 2r. 2 over 2r minus 1 minus 2 over 2r plus 1. And then that's also just equal to, that'll be 4r plus 2 minus 4r plus 2 over 4r squared minus 1, which is equal to 4 over 4r squared minus 1. Now that's the integral. That's basically the total area. So we'll call this total area. Now, if we're talking about essentially, right, if we're talking about error, we want to find this thing right here, this shaded area, okay, which is essentially just the total area subtracted by the area of one rectangle, okay, which will end up being 4 over 4r squared minus 1 over r squared, which will be 4r squared minus 4r squared minus 1 over 4r squared, or 4r to the 4 minus r squared, which is equal to, just call this error, which is equal to 1 over 4r to the 4 minus r squared to error. Okay, now note it says when when r is large. Now when r is large, if we're talking about like a polynomial or any sort of function of r, whenever r becomes large, we only care about leading order or leading power terms, which here the highest power term is 4. So we only care about the coefficient in front of 4. So we can ignore, essentially, since r is large, we can ignore r squared. Therefore, error is equal to 1 over 4r squared. And yeah, No, sorry, 1 over 4 r to the 4. Yeah, cool. Again, that's chill, right? That's literally, you've just gotten 16 marks in like what, maybe 10 minutes, right? That is, I think, literally up to there. You've just gotten 16 marks, and that you could literally just stop there and go to the next question. But then, obviously, for the sake of this video, we're going to do the whole question and we're going to do the last part. Now, I'm going to delete all of this because you don't really need the sketch for the last part. But yeah, so this last part is, I found to be quite tricky. I've already ranted about it, so I'm not going to get further into it. But essentially, think about what the error is, right? The error we discussed was the area minus the area. Well, basically, it was the integral minus the area of the rectangles, or the summation of the area of the rectangles, right? Um, and we know that the error is equal to 1 over 4r to the power of 4. So, and we want this summation here, right? And that's very, very similar to the error. So what if we took the summation of the error of all of the errors and then just multiplied by 4 to get this final result here, okay? And so if you do that, right, we'll get something like this. So we'll get the summation of r is 1 to infinity of 1 over 4r to the power of 4, right? But we know that the summation of all of the areas is just going to be the summation of um, of this summation here from 1 to infinity minus the integral from 1 to infinity. Okay, that's which is the same as this. Okay. Well, actually, it should probably be the other way around. Sorry. Which is the integral from 1 to infinity, or 1 minus a half, sorry, to infinity, 1 over x squared dx minus the summation from r is 1 to infinity of 1 over r squared. Okay, but what you realize is we don't actually have any term. We only have approximations of this thing right here. And we're given a value of e for which this converges. So we can't really use a starting factor of r equals 1. So what if we tried r equals 3? Okay. What if we tried let's just see what happens when we try it, okay? What if we tried r equals 3 and starting from r equals 3 instead of starting from r equals 1? Because we have an approximation for what e converges to, but if you plug this into here, you don't end up getting this, right? You don't end up getting that. So we've got to try something else, right? Why don't we start from r equals 3 and just see what happens, right? Okay, is equal to, wait, sorry, I should get rid of that because it starts with the integral. So it's the integral from 3 minus a half to infinity minus 1 over x squared dx minus the summation of 3 to infinity of 1 over r squared. Now, if we go into this, right, this is pretty much just equal to the summation of r equals 1 to infinity minus the summation of r equals 1 to 2. Okay, now what you're going to see is this happen. Great. Now, I probably should have kept this up from when we were approximating these values, But what you realize, okay, and if you go back to the part of where we approximated this final value, what you realize is this was how we approximated our third approximation. This was this, right? This was how we approximated this, right? So what now we can say is, sorry, these should all be approximation signs as well, right? So then what we can do is pretty much substitute 33 over 20 into this, and what we get is we get this, okay? And they said that this e value is approximately 1.645, and if you note in the question, e is essentially what r equals 1 to infinity converges to. So we can sub in our value of e into here as well, and we end up getting something like this. You get this, okay? Now, what this is 1.65, I believe. So it's 1.65 minus 1.645, which is equal to 0.05. So the summation from r equals 3 to infinity of 1 over 4 r to the 4, or essentially the summation of all of our errors from 3 to infinity is this, right? So if we multiply this by 4, we get the summation of 1 over r to the 4 from 3 to infinity. It's equal to 4 times 0.05. But we don't want that. We want the summation from r equals 1 onwards. So then all we just need to do is add on the first two terms of this summation, which is just which will just end up being this. But actually, these are all approximate signs. I don't know why I'm putting equals. These are all approximate signs. Will just end up being 1 plus 1 over 16 plus 0.2, which ends up being, I think, 1.8. Yep, which ends up being about 1.8. And that's literally, is it 1.8? I think it's 1. Unless I've gotten something wrong. I think it's 1.08. Yeah, 1.08. Yes. Because 1 over 16 is, yeah, that's 1.08. Cool. Anyways, that's the whole question done. Honestly, I know I said just put r equals 3 and hope it works. Well, if you're in an exam, right, the first thing you would automatically try and do is try and make r equals 1 and then see if r equals 1 works. And you could make, and obviously we know that e converges to 1.645, so you could sub an e here, right, and then try this integral and try and see what you get. But what you get, you don't end up getting this answer at the end. Then you try r equals 2, you don't get it. Then you try r equals 3, and then when you try r equals 3, then it eventually works. So I went straight to doing r equals 3. But there is, I think, an element of trying some trial and error in this question, and just because you have so much time in step, you just need to try stuff out. But yeah, I mean, this question was a bit hard to explain. I think part two. I am a bit new to like making these videos, so if you're like stuck on anything, just comment below and I'll do my best to answer it. But I do think part one and the sketch and everything else is they're, I would say, fairly accessible marks you can get if you just think about it long enough. And yeah, cool. So let's go to the examiner report. Surprisingly, the examiner report doesn't mention anything about the final part of this question. It just mentions that most people found errors in the approximations itself, which I'm a bit surprised about because I mean it's not easy, but I thought the final part was much harder than the approximations. But okay, let's get into it. So first task in this question was generally well answered, although sketches were often unclear and hard to interpret. In part one, many candidates were often able to obtain the first approximation, but then cannot see how to achieve the other two. Okay, The other two, I just think if you have a summation and you have an integral, or you have a summation something, just evaluate the terms, right? Just you start from r equals 1 and then you approximate further, and you just manipulate your approximations, right? If you have one sort of formula and you have three different forms that you can get out, it's just manipulating what you know, what you've proved. You're just manipulating it. You're trying to take out different terms of the summation and then add on the rest of the terms as an approximation with that integral. But yeah, that's literally all you have to do. I think if you just spend enough time looking at it, you'll get there eventually. And then those who successfully completed part one were often able to approximate the error in part two and see how it applies to the final sum. Well, I couldn't, because I was able to do part one, but I could not do the final part of part two, so I did not know what they're on about. But yeah, maybe I'm just terrible. Who knows? Anyways, thank you for watching. If you didn't understand some of that, just drop it in the comments. I'll try my best to answer it. And yeah, thank you very much. I will be probably doing a step three video next, because I found a quite nice step three question to do. I still have to do the induction one from 2015, because I haven't gone on to that one yet. But anyways, I'll go on to it. But yeah, thank you for watching. Bye bye.